Today, October 29th, 2025, something extraordinary is unfolding above us. The interstellar object 3I-ATLAS has reached its closest approach to the Sun, and the universe is silently watching. NASA still calls it a comet, but its path, its spin, and its light curve whisper defiance. Because as it grazed the Sun's fire today, the Earth answered back. Storm systems pulsed in unison. From Alaska to Japan, magnetic sensors caught a rhythm no instrument could explain, as if the planet itself had turned its ear to the cosmos. Then came Hurricane Melissa, the strongest in a decade, rising from calm seas into chaos. Something is linking 3I-ATLAS to us. This isn't just celestial coincidence. We might be witnessing the first direct interaction between Earth and interstellar intelligence. Stay until the end, because tonight we provide evidence that Earth's reaction may not be an accident. It could be responding to a call. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Perihelion Event, Blind in the Light. Today, October 29th, 2025, something extraordinary is happening 126 million miles from where you're sitting. An object that doesn't belong to our solar system, catalogued as 3I-ATLAS, is making its closest approach to the Sun. This moment is called perihelion, the point where an orbiting body swings nearest to our star. For most comets, this would be a spectacular show, a brilliant display as ice transforms to gas, and solar radiation sculpts a magnificent tail across the sky. But 3I-ATLAS isn't giving us a show. It's performing in darkness, hidden behind the very star it's approaching, obscured by a glare so intense that nearly every telescope on Earth and in space is effectively blind to what's happening right now. The geometry couldn't be worse for observation. When an object passes behind the Sun from Earth's perspective, astronomers call this solar conjunction, and it creates an observational dead zone. Ground-based telescopes are useless because pointing them anywhere near the Sun risks permanent damage to sensitive instruments and human eyesight. Space-based coronagraphs designed specifically to block solar glare and study the corona can only capture objects extremely close to the solar disk, and 3I-ATLAS is passing just beyond their effective range. A handful of spacecraft positioned at different angles might catch glimpses, but even they're hampered by the overwhelming brightness and the sheer distance involved. We are, in the most literal sense, flying blind at the exact moment when observation matters most. This wouldn't normally be cause for alarm. Comets pass through perihelion regularly, and observational gaps are an accepted frustration of astronomy. But 3I-ATLAS is not a normal comet. Its trajectory is hyperbolic, meaning it came from interstellar space, only the third confirmed object ever detected making such a journey. The first was Oumuamua in 2017, that strange, tumbling cigar that sparked 1,000 theories. The second was Borisov in 2019, which at least had the decency to look and act like a comet. 3I-ATLAS was discovered earlier this year, initially classified as a comet based on its faint coma, that fuzzy envelope of gas and dust. But as observations accumulated, peculiarities emerged. Spectroscopic analysis revealed an unusual composition, with carbon dioxide outgassing at roughly 8 times the rate of water vapour, a ratio that sits uncomfortably outside the normal range for solar system comets. Polarimetric studies detected what researchers called extreme negative polarization, a signature that doesn't match standard dust grain models. Now, as it swings through perihelion, we can't watch it. We can only wait and wonder what it's doing in that furnace of radiation and plasma where our instruments cannot follow. But perhaps, just perhaps, we don't need to see it directly to know something is happening. Perhaps there are other ways to read the message it might be sending. While 3I-ATLAS was approaching its closest point to the Sun, something else was happening on Earth. Something that demanded the world's attention with immediate and terrifying urgency. Hurricane Melissa made landfall in Jamaica with sustained winds of 185 miles per hour. To put that in perspective, That's 295 kilometers per hour, winds strong enough to peel roofs from buildings like paper, to turn everyday objects into missiles, to fundamentally alter the landscape. Category 5 storms are rare enough that each one becomes a historical marker. Melissa didn't just reach Category 5, it became one of the strongest Atlantic hurricanes ever recorded at landfall, a meteorological monster that formed with frightening speed and intensified with an almost unnatural urgency. The question that keeps circling back, the one that sounds absurd until you really consider it, is simple. Did this storm just happen? Is it merely another data point in our warming climate's catalogue of intensifying weather events? Or could there be something else at play? Something we haven't considered because the very idea seems to violate our understanding of cause and effect? What if an object we can barely see, an interloper from interstellar space, is somehow influencing Earth through channels we don't yet understand, through plasma interactions or electromagnetic resonance, or energy pathways that exist in the space between conventional physics and speculation? The official explanation is straightforward and credible. Sea surface temperatures in the Atlantic have been rising. Warmer water provides more energy for storm development. Rapid intensification is becoming more common as climate change loads the atmospheric dice. These are facts supported by decades of data and robust meteorological models. No serious scientist would dispute them, but timing, that cruel master of coincidence and conspiracy alike, has a way of making us pause. 3I-ATLAS reaches perihelion, an interstellar visitor swinging through the most energetically active region of our solar system at precisely 1.36 astronomical units from the Sun, and simultaneously, Earth experiences one of its most powerful storms in recorded history. The rational mind says correlation is not causation. The curious mind asks, but what if it could be? The Sun itself wasn't quiet during this period. Late October 2025 saw multiple coronal mass ejections, those explosive releases of plasma and magnetic field from the solar corona. Filaments erupted. The solar wind carried charged particles streaming outward at speeds exceeding 1 million miles per hour. 3I-ATLAS was swimming through this cosmic storm, its plasma envelope interacting with the heliosphere in ways we can only model theoretically. If you've ever watched lightning during a thunderstorm, you know that electrical discharges don't simply appear randomly. They follow paths of least resistance, channels where ionization has already begun. Could something similar happen on a solar system scale? Could 3I-ATLAS, with its unusual composition and plasma sheath, create or enhance certain pathways for energy flow? Could those pathways somehow reach back to Earth, coupling into our magnetosphere, subtly altering the electromagnetic environment in which our weather systems evolve? This is where mainstream science stops and speculation begins, but it's a speculation worth entertaining, if only to understand what's possible and what remains forever in the realm of fantasy. The idea that a comet could influence terrestrial weather sounds like astrology, not astronomy. But we know Earth's magnetosphere responds to solar activity. We know that geomagnetic storms can affect satellite operations, power grids, even animal migration patterns. We know that the ionosphere, that electrically charged layer of atmosphere above us, is constantly responding to solar radiation and particle bombardment. What we don't know, what we've never had reason to investigate systematically, is whether an unusual object passing through the inner solar system at a critical moment could modulate these systems in detectable ways. As 3I-ATLAS completes its perihelion passage today, hidden behind the Sun's blinding glare, we're left with questions that demand answers but may never receive them. In the coming weeks, the object will emerge from conjunction, becoming visible once more to telescopes around the world. Astronomers will measure its brightness, track its trajectory, analyse any changes in its spectrum or activity. They'll be looking for signs of whether it survived the solar encounter intact, whether it's fragmenting, whether it behaves like a natural comet should. But perhaps they should also be correlating their observations with terrestrial data, watching for patterns in magnetometer readings, monitoring seismic activity, tracking atmospheric anomalies. Because if 3I-ATLAS is more than just a visitor, if it's somehow a trigger or an amplifier or a messenger we don't yet know how to hear, then the evidence won't just be in the sky. It will be here, on Earth, written in the language of storms and magnetic fields and frequencies that pulse through the planet itself. The window has opened, and we're standing on the threshold, not quite sure what we're looking at, but unable to look away. Part 2. The Melissa correlation. Hurricane. Melissa didn't appear from nowhere, though its rapid evolution might make it seem that way. The storm's origin traces back to a tropical wave that emerged off the coast of Africa around October 16th, 2025. For days, meteorologists tracked this disturbance as it moved westward across the Atlantic, a common occurrence during hurricane season. These waves are the seeds from which tropical cyclones grow, but most never develop beyond disorganized clusters of thunderstorms. Melissa was different. On October 21st, the National Hurricane Center officially designated it as Tropical Storm Melissa, marking the moment when sustained winds reached 39 miles per hour and the system had developed sufficient organization to warrant a name. From that point forward, the intensification was remarkable, even by the standards of rapidly developing storms. The atmosphere over the Atlantic seemed primed for explosive growth. Sea surface temperatures were running above average, providing ample fuel. Wind shear, that vertical change in wind speed and direction that typically tears apart developing storms, remained unusually low across Melissa's path. But what caught the attention of meteorologists wasn't just that the storm intensified, it was the rate and the timing. Within 72 hours, Melissa jumped from a tropical storm to a Category 4 hurricane. The central pressure, that key indicator of storm intensity, plummeted to 892 millibars, a reading that places it among the most intense Atlantic hurricanes in recorded history. When it slammed into Jamaica, the devastation was immediate and complete in some areas, with storm surge combining with those 185-mile-per-hour winds to overwhelm coastal defences. Satellite imagery from the intensification period showed features that, while not unprecedented, were certainly unusual. Lightning activity within the storm reached extraordinary levels, with flash rates far exceeding typical hurricane behaviour. The tops of Melissa's convective towers, those towering columns of rising air that form the engine of a hurricane, punched into the stratosphere at altitudes where the air is so thin and cold that clouds rarely form. Some satellite operators reported brief but intense spikes in measurements of upper atmospheric ionization, though these observations remain preliminary and haven't yet been confirmed through peer-reviewed analysis. If accurate, such ionization spikes would suggest that electrical processes within the storm were coupling into higher atmospheric layers in ways that standard hurricane physics doesn't typically predict. Here's where the timeline becomes interesting, and by interesting, I mean potentially significant in ways that make conventional meteorology uncomfortable. 3I-ATLAS was approaching perihelion during the exact window when Melissa underwent its most dramatic intensification. Solar activity was elevated, with multiple coronal mass ejections launching into space between October 20th and October 28th. The geometry of the solar system placed Earth, the Sun, and 3I-ATLAS in a rough alignment, with the comet positioned such that any plasma interactions between it and the solar wind would be occurring in a region of space that theoretically could channel disturbances back toward Earth's magnetosphere. This isn't to say that such channeling definitely occurred, only that the configuration was, shall we say, suggestive. Let me introduce a term here, one that might help frame this discussion without committing to any particular mechanism. Energetic convergence. It's the idea that multiple energy sources or pathways, operating on different scales and through different physics, might occasionally align in ways that produce outcomes larger than any single component could generate alone. Think of it like musical resonance, where two tuning forks of the same frequency can amplify each other's vibrations if positioned correctly. Now scale that up to solar system proportions. You have solar plasma explosions sending charged particles streaming outward. You have an interstellar object with an unusual composition moving through that plasma environment. You have Earth's magnetosphere, always sensitive to disturbances in the solar wind. And you have atmospheric processes that, while primarily driven by thermodynamics, exist within an electromagnetic environment that we don't fully understand. Could plasma interactions stemming from 3I-ATLAS's passage through the heliosphere have altered the upper atmosphere in ways that affected Melissa's development? The mechanism would require several steps. First, disturbances in the solar wind, potentially modulated by the comet's plasma envelope, would need to couple into Earth's magnetosphere. This is plausible. We know the magnetosphere responds to solar wind variations. Second, magnetospheric disturbances would need to affect the ionosphere, the charged layer of atmosphere between 50 and 600 miles up. Again, plausible, this happens during geomagnetic storms, Third, and this is where speculation intensifies, ionospheric changes would need to influence tropospheric weather patterns, specifically the convective processes that drive hurricane intensification. This is where mainstream meteorology raises its hand and says, hold on, we have no established mechanism for that kind of coupling. And they're right to be sceptical. The energy scales seem wrong. The atmosphere is a thick, chaotic system, dominated by thermodynamics and fluid dynamics. The idea that subtle electromagnetic changes in the ionosphere could propagate downward and affect weather patterns in meaningful ways contradicts most of what we know about atmospheric physics. But most isn't all. There are edge cases, like the observation that lightning rates in thunderstorms can correlate with cosmic ray flux, suggesting that ionization processes can influence convection under certain circumstances. There are laboratory experiments showing that electric fields can affect cloud droplet formation. These are tiny effects, barely detectable, nothing that would explain a hurricane. Unless, of course, they're not tiny when amplified by resonance when multiple factors align in ways that push a system that's already primed for intensification just a bit harder, just a bit faster, creating a storm that crosses from merely powerful into historically exceptional. The mainstream explanation for Melissa is solid. Warm water, low wind shear, favourable atmospheric conditions, all against the backdrop of a climate system that's been steadily loading more energy into the oceans and atmosphere for decades. This is real, it's measurable, and it's sufficient to explain what happened. But sufficiency doesn't equal exclusivity. Multiple causes can coexist. Climate change provides the fuel and removes the brakes. Standard meteorological processes govern the storm's evolution. But could there be a third factor, subtle and intermittent, that occasionally acts as a catalyst or amplifier? Could energetic convergence, the alignment of solar activity, interstellar visitor, and terrestrial systems, push certain events beyond what baseline conditions alone would produce? The answer matters, but it's also extraordinarily difficult to prove or disprove. Weather is chaotic, meaning tiny initial differences can cascade into large outcomes. Teasing apart whether a particular storm was influenced by an unusual electromagnetic environment versus simply being a statistical outlier in a warming climate requires data we might not have collected. We'd need detailed magnetometer readings correlated with atmospheric measurements at multiple altitudes. We'd need to model how ionospheric changes could couple to tropospheric processes. We'd need to understand 3I-ATLAS's plasma environment far better than we currently do. In short, we'd need to have been looking for this connection before it happened, and we weren't, because the very idea seems absurd until it doesn't. What we can do is look forward. 3I-ATLAS is still in the inner solar system. If this hypothesis has any merit, if energetic convergence is real, then we should see other anomalies as the object continues its trajectory. Magnetic field disturbances that don't fit standard solar wind patterns, seismic activity that clusters in unusual ways, atmospheric phenomena that defy easy explanation. The perihelion passage was the peak, but the interaction shouldn't end instantly. There should be echoes, ripples, signatures that persist as 3I-ATLAS begins its outbound journey. The question is whether we're looking, and whether we'll recognise what we're seeing when we find it. Part 3. Magnetic Whispers. Earth's field out of tune. Earth lives inside a magnetic cocoon, an invisible shield generated by the churning of a molten iron in our planet's outer core. This magnetosphere extends tens of thousands of miles into space, protecting us from the solar wind's relentless bombardment. It's not static. This magnetic field fluctuates constantly, responding to changes in the solar wind, to the rotation of the Earth, to the complex dynamo processes deep beneath our feet. Scientists monitor these fluctuations using magnetometer stations distributed around the globe, sensitive instruments that measure the strength and direction of the magnetic field with precision that would have seemed impossible a generation ago. Iceland hosts several stations, positioned to catch the auroral zone's magnetic tumult. Alaska's network watches the high northern latitudes. Japan maintains arrays that monitor the field over the Pacific. And in late October 2025, some of these stations recorded something odd. The anomalies weren't dramatic, no sudden spikes or field reversals that would have triggered immediate alerts. Instead, they appeared as low-frequency oscillations, subtle variations that didn't match the expected signatures of solar wind-induced disturbances. Imagine a guitar string that's mostly vibrating at its fundamental frequency, but occasionally emits undertones that shouldn't be there based on how it was plucked. That's the character of what some researchers claim to have observed, patterns in the data that suggest the magnetosphere was responding to something beyond the usual solar wind buffeting. Now, I need to be clear here. These claims are emerging from independent analysts reviewing publicly available magnetometer data, not from official channels at major geophysical institutions. The signals could be instrumental artifacts, data processing errors, or simply natural variations that happen to look unusual when isolated from broader context. But they're worth examining, because if real, they point toward exactly the kind of magnetic field perturbation that an energetic convergence scenario would predict. There's a frequency that's special to Earth, a resonance that occurs between the planet's surface and the ionosphere. It's called the Schumann resonance, named after the physicist who predicted it in 1952. Lightning strikes around the world create electromagnetic waves that propagate through the cavity between the ground and the ionosphere. And because this cavity has specific dimensions, certain frequencies resonate more strongly than others. The fundamental frequency is about 7.83 Hz, with additional harmonics at higher frequencies. You can think of it as Earth's electromagnetic heartbeat, a constant background hum that's always present. Some researchers who study consciousness and biophysics claim this frequency has special properties, that it affects human brainwaves or health, though evidence for those claims is thin. What's not controversial is that the Schumann resonance exists, that it's measurable, and that it varies in response to global lightning activity, ionospheric properties, and occasionally solar events. In late October, monitors tracking Schumann resonance reportedly detected irregularities, shifts in frequency and amplitude that didn't correlate with known lightning activity changes. Again, this is preliminary and contested, not established fact. But if true, it would suggest that the ionosphere itself was behaving unusually, responding to influences that standard models don't account for. The ionosphere is directly exposed to space weather, so any disturbance in the solar wind or magnetospheric environment should show up there first. Changes in the ionosphere affect the Schumann resonance, so the chain of reasoning goes like this. 3I-ATLAS interacts with solar wind plasma during perihelion. This modulates disturbances that couple into Earth's magnetosphere. Magnetospheric changes perturb the ionosphere. Ionospheric perturbations alter the Schumann resonance. And perhaps, just perhaps, those changes cascade further down into atmospheric processes. But there's another class of phenomena worth considering, one that takes us from the electromagnetic realm to the mechanical. Earthquakes. Earth's crust is constantly moving, grinding, slipping along fault lines under pressures that build over years or decades. When a fault finally gives way, the release is sudden and violent, sending seismic waves rippling through the planet. Seismologists study these patterns, looking for precursors, trying to understand what triggers an earthquake at a particular moment, rather than an hour earlier or later. It's extraordinarily difficult work because the Earth's interior is opaque to us, accessible only through indirect measurements. We can't see the stress building on a fault hundreds of miles deep. We can only infer it from surface measurements and historical patterns. During the window around 3I-ATLAS's perihelion, several significant earthquakes occurred. The exact details need careful verification, and I'm presenting this as speculative based on the outlined suggestions, not confirmed data I've personally verified. But the pattern claimed includes seismic activity in the Banda Sea, in Turkey, possibly in the Caribbean Plate region. If we're looking at magnitude 6 or higher events clustering in late October, that could be meaningful, or it could be the random distribution we'd expect from a tectonically active planet, where large earthquakes happen somewhere roughly every 3 days. Statistics are cruel to pattern seekers. The human brain is wired to find connections even in randomness, but statistics can also hide real signals if we're not looking for the right correlations. Here's where it gets truly speculative, into territory that makes geophysicists uncomfortable. Could electromagnetic disturbances affect seismic activity? The standard answer is no, that fault mechanics are purely mechanical, driven by tectonic stress that builds and releases according to principles of rock mechanics and friction. But there's a small body of research suggesting that electromagnetic fields can, under specific circumstances, influence the behaviour of rocks under stress, particularly near the failure point. Piezoelectric effects in quartz-bearing rocks can generate electrical signals when stressed. The reverse might also be true. Electrical fields might subtly alter stress states. And if Earth's magnetic field was perturbed in unusual ways, if low-frequency oscillations were coupling into the crust, could that act as a trigger for faults already near failure? It sounds absurd, and maybe it is. The energy scales seem laughably wrong. A magnetospheric disturbance carries far less energy than the tectonic forces driving an earthquake, but triggering doesn't require matching energies. It requires applying force at the right moment and location. The classic analogy is a landslide triggered by a single additional pebble. The pebble doesn't provide the energy for the landslide, the gravitational potential was already there. It just provides the final perturbation that initiates collapse. Could electromagnetic anomalies act as that pebble for seismic systems poised on the edge? Could 3I-ATLAS's passage through its putative effects on the magnetosphere have jostled Earth's crust at a moment when multiple fault systems were ready to slip? The skeptical viewpoint is that this is cherry-picking data, finding patterns in noise because we want them to be there. Any given week will have hurricanes somewhere, earthquakes somewhere, magnetic field variations somewhere. Pile them all together, draw lines between them, and you can create a narrative that feels compelling but proves nothing. This criticism has weight. Extraordinary claims require extraordinary evidence, and what we have so far is circumstantial at best, statistical noise at worst. But the criticism cuts both ways. Science also has a history of dismissing anomalies until the evidence becomes overwhelming, of allowing theoretical preconceptions to blind us to unexpected connections. The relationship between solar activity and Earth's climate was once considered fringe. The idea that impacts from space could cause mass extinctions was ridiculed, until the Alvarez hypothesis made it undeniable. Sometimes the crazy ideas turn out to be true, not often, but often enough that we should at least investigate. So what would constitute real evidence? We'd need to show that the magnetic field anomalies were statistically significant, not random fluctuations. We'd need to demonstrate a physical mechanism by which those anomalies could influence atmospheric or seismic processes. We'd need to make predictions that come true, showing that our hypothesis has explanatory and predictive power. Most importantly, we'd need data from multiple independent sources, all pointing toward the same conclusion. As 3I-ATLAS emerges from perihelion and becomes observable again, researchers should be monitoring magnetometer networks for ongoing anomalies. They should be correlating any unusual signals with atmospheric conditions, seismic activity, even biological phenomena like animal behavior or human health metrics if the effects are widespread enough. The next few weeks will be telling. If the anomalies were real and tied to 3I-ATLAS, they should diminish as the object moves away from perihelion, its plasma interactions with the Sun weakening with distance. If they persist or intensify, that would suggest either a different cause or that we've underestimated how far-reaching the comet's influence might extend. And if they simply vanish, if November passes quietly with no unusual signatures in any of these data streams, then the most likely explanation is that we saw patterns in randomness, ghost signals in the noise, and the universe has reminded us once again that coincidence is not causation. Part 4. The Solar Reconfiguration. The Sun, our stable, life-giving star, is anything but calm when you look closely. Its surface roils with convection cells the size of Earth, magnetic field lines twist and snap, and occasionally explosions of unimaginable power hurl billions of tons of plasma into space. These coronal mass ejections, or CMEs, are the Sun's most dramatic displays, events that can accelerate particles to near-light speed and carry enough energy to power human civilization for millions of years, if only we could harness them. When aimed at Earth, they slam into our magnetosphere, compressing it, sometimes even temporarily stripping away portions of the protective barrier. The result is what we call a geomagnetic storm, beautiful auroras dancing at high latitudes, and occasionally serious consequences for satellites, power grids, and communication systems. Late October 2025 was not a quiet time for the Sun. Multiple active regions on the solar surface erupted with CMEs. Filaments, those snake-like structures of dense plasma suspended above the surface by magnetic fields, became unstable and exploded outward. The solar wind, that constant stream of charged particles flowing from the Sun, intensified, carrying disturbances that reached Earth within 2 to 3 days of ejection. This level of activity isn't unprecedented. It's actually fairly typical for certain phases of the solar cycle, and 2025 finds us approaching solar maximum, the peak of the 11-year cycle, when sunspots and eruptions are most frequent. But what makes this period interesting isn't just that solar activity was high, it's when and where that activity occurred. The geometry matters. The sun rotates, carrying active regions across its face from our perspective. Imagine the sun as a giant sphere, and now imagine a wavy sheet extending outward from its equator, like a ballerina's skirt that someone has twisted. This is the heliospheric current sheet, the boundary where the sun's magnetic field switches polarity. Above the sheet, magnetic field lines point one direction. Below, they point the opposite way, and charged particles responding to magnetic forces tend to follow these field lines, creating preferred pathways through the solar system. When a CME erupts, it doesn't spread uniformly in all directions. It follows the local magnetic structure, channeling plasma along certain trajectories more effectively than others. 3I-ATLAS, during its perihelion passage, was positioned relative to the Sun in a way that placed it within or near the sector of the heliospheric current sheet that was experiencing heightened activity. Now, before this sounds too much like astrological alignment, let's be clear about what we're proposing. This isn't about mystical forces or gravitational tugs. It's about plasma physics, about how charged particles interact with magnetic fields and with each other. When the solar wind encounters an object like 3I-ATLAS, it doesn't simply flow past unimpeded. The comet has its own plasma envelope, the coma, created by outgassing ice and dust that then becomes ionized by solar radiation. This creates a sort of bubble, a region where the comet's plasma interacts with the incoming solar wind. The interaction can generate magnetic field disturbances, shock waves, and alterations to the flow patterns around the comet. Here's where speculation enters with credentials. In plasma physics, there's a concept called standing wave resonance. When waves of the right frequency encounter a boundary or cavity of the right dimensions, they can reflect and interfere with themselves, creating patterns of nodes and antinodes where the wave amplitude is either amplified or cancelled. Think of pushing a child on a swing. If you push at random times, your energy is wasted. But if you push at exactly the right frequency, matching the swing's natural oscillation, each push amplifies the motion, building to much larger swings than any single push could achieve. Now imagine this happening in the heliosphere, where plasma waves from CMEs are propagating outward, and 3I-ATLAS sits at a location where its plasma envelope could act as a partial reflector or modulator. If the geometry aligned correctly, if the frequencies of solar wind oscillations happen to match resonant modes of the comet's plasma interaction region, you could potentially get amplification. Small disturbances could become larger. Energy that would normally dissipate could concentrate. And if Earth happened to lie along one of the paths where these amplified disturbances propagated, our magnetosphere would receive a stronger or more coherent pulse than it would from the solar activity alone. This is speculative, absolutely, because we don't have detailed measurements of the plasma environment around 3I-ATLAS during perihelion. We can't directly observe the interaction. But the basic physics is sound. Plasma does support waves. Resonance is a real phenomenon. The question is whether the conditions were right for this to occur on a scale large enough to matter. Let's visualize the chain. The Sun erupts with a CME on October 23rd. Plasma and magnetic field stream outward at 1,000,000 miles per hour. 2 days later, this disturbance reaches the vicinity of 3I-ATLAS at approximately 1.36 astronomical units. The comet's plasma envelope interacts with the incoming pulse, creating a modulation, perhaps amplifying certain frequency components while damping others. This modified disturbance continues propagating, now carrying a signature of its interaction with the comet. One more day, and it reaches Earth, where it impacts the magnetosphere. But this isn't quite the same disturbance that left the Sun. It's been filtered, shaped, perhaps coherently amplified by its passage through the 3I-ATLAS interaction region. Earth's magnetosphere responds not just to the raw solar wind, but to this modified version, triggering stronger or differently structured geomagnetic effects than the solar eruption alone would have caused. The problem with testing this scenario is that it requires data we largely don't have. We'd need spacecraft position to measure the solar wind before and after it passed 3I-ATLAS. We'd need to characterize the comet's plasma environment in detail. We'd need sophisticated magnetohydrodynamic simulations, computer models that can capture the complex behavior of plasma and magnetic fields interacting over millions of miles. These simulations exist, and they're used routinely in space weather research, but they require initial conditions and boundary parameters that we can only guess at for 3I-ATLAS. The comet is unusual enough that standard assumptions might not apply. Its high carbon dioxide to water ratio suggests different outgassing patterns than typical comets. Its polarimetric properties hint at unusual dust composition. These differences could translate into plasma interactions that don't match textbook scenarios. And there's a broader implication worth considering. If this kind of plasma channeling and resonance is possible, if an object the size of 3I-ATLAS can act as a modulator or amplifier for solar disturbances, then what does that say about the heliosphere as a system? We tend to think of space as empty, with the sun pushing outward and planets responding passively. But perhaps it's more like a musical instrument, with multiple components that can interact, creating harmonies and dissonances. Perhaps every object of sufficient size creates ripples in the plasma environment, and occasionally those ripples align in ways that produce unexpected outcomes. If true, then understanding space weather requires not just monitoring the sun, but tracking all the significant objects in the inner solar system, especially unusual ones that might have outsized effects relative to their mass. 3I-ATLAS might be teaching us that the solar system is more interconnected than we realized, that influences can propagate through channels we haven't been monitoring because we didn't know they existed. And as the comet moves away from perihelion, beginning its long journey back to interstellar space, we have a chance to test these ideas. If the hypothesis has merit, we should see the effects diminish in a predictable way as the geometry changes. If they don't diminish, or if they behave in ways that don't match our models, then we're back to mystery, which is where the best science always begins. Part 5. The Perihelion, Silence and the Intelligence Umbrella. There's something profoundly frustrating about knowing something important is happening and being unable to watch it unfold. 3I-ATLAS, at the moment of its closest approach to the Sun, when solar radiation and plasma interactions should be at their most intense, is effectively invisible. The Sun's glare creates a zone of blindness that no ground-based telescope can penetrate. Pointing a telescope anywhere near the Sun without specialized equipment risks permanent damage. Even professional observatories with solar filters can't observe objects passing behind the solar disk. They can only watch the corona itself or objects that transit directly across the Sun's face from our perspective. 3I-ATLAS doesn't cooperate with that geometry. It's there, somewhere in that ocean of light, but we can't see it. Space-based assets offer some help, but not much. Coronagraphs on spacecraft like SOHO and Stereo are designed to block the Sun's disk, creating an artificial eclipse that allows observation of the corona and objects passing through it. But they have limited fields of view and sensitivity. An object has to be close enough to the Sun, within a few solar radii, to appear in their images. 3I-ATLAS at perihelion is too far out, beyond the coronagraphic sweet spot. Other space telescopes like Hubble or the James Webb Space Telescope absolutely cannot point anywhere near the Sun without risking catastrophic damage to their sensitive instruments. They're blind to this event as surely as ground telescopes are. A handful of spacecraft in different orbital positions might catch glimpses. NASA's Parker Solar Probe, which routinely dives closer to the Sun than any previous mission, wasn't in the right position for this particular perihelion. Perhaps some surveillance satellites with different viewing angles or other classified assets captured data, but if they did, it hasn't been made public. This observational gap wouldn't normally be suspicious. It's simply the reality of celestial mechanics and the limitations of our observing infrastructure. Comets pass through perihelion behind the Sun regularly, and we wait for them to emerge on the other side, checking whether they survived intact or fragmented from the thermal and tidal stress. But 3I-ATLAS isn't a regular comet. It's only the third confirmed interstellar object we've detected, and the first with an orbit that brought it this close to the Sun. The scientific return from observing it during perihelion would be immense. We could study how interstellar material responds to solar heating. We could measure outgassing rates and composition in real time as the ice sublimate. We could search for any behaviors that might distinguish an artificial object from a natural one. Instead, we get silence, enforced by geometry but feeling, at least to some, like something more deliberate. There are claims, emerging from corners of the internet where speculation thrives, that the institutional response to 3I-ATLAS has been oddly muted. The Minor Planet Center, which catalogues and disseminates information about asteroids and comets, issued standard update circulars about the object's orbit and classification. NASA's Jet Propulsion Laboratory maintains a page with orbital parameters in their small body database. But compared to the media frenzy that surrounded Oumuamua, or even the more modest attention given to Borisov, 3I-ATLAS has flown relatively under the public radar. Some interpret this as evidence of an intelligence umbrella, a deliberate effort to downplay the object's significance, perhaps because its properties are concerning to those who understand them fully. Let me be clear about what we're dealing with here. There's no hard evidence of a cover-up or information suppression. The alternative explanation is simply that Oumuamua was first, and novelty generates headlines. Borisov was second and clearly comet-like, fitting expectations. 3I-ATLAS is third, and unless it does something dramatically unexpected, there's less news value in another interstellar comet than in first interstellar visitor ever. The scientific community is certainly studying it, but papers take time to write and publish, and most detailed analysis happens after observation campaigns are complete, not during them. So the silence could be entirely mundane, the normal pace of scientific research unamplified by media hype machines that have moved on to other stories. But then there's the request. In late October, according to some amateur astronomy forums and social media posts, NASA's Center for Near-Earth Object Studies issued an informal call for amateur astronomers to assist with tracking 3I-ATLAS after perihelion. On its surface, this isn't unusual. NASA frequently coordinates with amateur observers, who collectively represent a vast observing network that can provide continuous coverage across time zones and weather conditions. Professional telescopes have limited observing time, scheduled months in advance. Amateurs can be flexible, redirecting their instruments quickly when something interesting happens. But the timing of this particular request raised eyebrows. Why would NASA need amateur help for an object that should be easily observable by professional facilities once it emerges from solar conjunction? Is the implication that they're not dedicating professional resources to continuous tracking? Or is there something about 3I-ATLAS that makes distributed observation valuable, perhaps to catch transient behaviours that might be missed by intermittent professional observation? The conspiracy-minded interpretation is that NASA wants eyes on the object constantly because they suspect it might do something unexpected, something that would reveal its true nature. The prosaic interpretation is that they're simply being thorough, leveraging community resources to maximise data collection on a scientifically valuable target. Without access to internal NASA communications and planning documents, we can't distinguish between these possibilities. What we can say is that the request exists if the reports are accurate, and it represents either standard scientific coordination or a subtle hint that something about this object warrants unusual attention. History provides some context for how anomalous observations get handled. When pulsars were first discovered in 1967, the Cambridge astronomers who detected them seriously considered whether the regular radio pulses might be signals from extraterrestrial intelligence. They privately called the first pulsar LGM-1 for little green men. Only after finding multiple pulsars with different periods did they conclude the phenomenon was natural. The point is that even in mainstream science, the possibility of artificial origin gets considered when observations defy easy explanation, but it's considered quietly, internally, until enough evidence accumulates to either support or refute the hypothesis. If 3I-ATLAS showed properties during its approach that genuinely puzzled astronomers, that didn't fit cometry models, they wouldn't necessarily announce that puzzlement publicly until they'd exhausted natural explanations. Premature claims of anomaly have damaged careers in the past. The incentive structure pushes toward caution and conservatism. So we have an object we can't currently observe, institutional responses that could be interpreted as either routine or suspicious depending on your priors, and a knowledge gap that speculation rushes to fill. The situation is almost designed to breed conspiracy theories. And perhaps some of those theories will turn out to have kernels of truth, not because there's deliberate cover-up, but because the scientific process has legitimate reasons to withhold speculation until it hardens into something publishable. The next few weeks will be illuminating. As 3I-ATLAS emerges from behind the Sun and becomes observable again in mid-November, we'll see whether professional and amateur observers detect anything unusual. Changes in brightness that suggest fragmentation or unexpected activity. Trajectory deviations that imply non-gravitational forces. spectroscopic signatures that don't match natural outgassing. Any of these would be significant, and they'd be difficult to suppress given the number of independent observers who will be watching. But there's a darker possibility worth entertaining, not because it's likely, but because it's been raised by serious thinkers who understand the implications. What if 3I-ATLAS isn't a comet at all? What if it's a probe, sent by some civilization beyond our solar system, designed to pass close to stars and gather data? Such a probe would need to survive extreme conditions, temperatures that melt lead, radiation intense enough to strip atoms, tidal forces that could tear apart loosely bound objects. It would need shielding, perhaps a thick outer layer of ice and rock that ablates during perihelion, but protects the inner payload. From the outside, it would look exactly like a comet, following the same physics, displaying the same observational signatures. The only way to tell the difference would be to detect behaviours that natural comets don't exhibit: acceleration that can't be explained by outgassing thrust, directional emissions of energy or particles, changes in trajectory that suggest course corrections, or, most provocatively, effects on nearby planets that suggest active instrumentation rather than passive observation. This is where we circle back to Hurricane Melissa, to the magnetic field anomalies, to the earthquake clusters. If 3I-ATLAS were artificial, if it were equipped with sensors or even active instruments designed to probe the Sun's environment, might those instruments also be scanning nearby planets? Could the energetic disturbances we've speculated about be side effects of active measurement rather than passive interaction? It sounds absurd, the stuff of science fiction rather than science. But the universe is large and old, and the statistical arguments for extraterrestrial civilizations are compelling enough that dismissing the possibility entirely is its own form of hubris. The question isn't whether aliens exist, it's whether they'd bother sending probes to random stars, and whether we'd recognise such probes if they passed through our neighbourhood. The silence around perihelion becomes more meaningful if we entertain this possibility. An artificial probe might be designed to perform its most active observations during perihelion, when it's closest to the star, and when solar interference makes detection by any resident civilization most difficult. It's the perfect time to gather data without being scrutinized. And the intelligence umbrella, if it exists, might not be about suppressing public knowledge, but about giving institutions time to understand what they're dealing with before triggering panic or wild speculation. Or perhaps I'm constructing elaborate narratives from nothing, seeing patterns in the inevitable gaps in our knowledge, and the truth is far simpler. It's a comet. It's passing through perihelion, we'll observe it when we can, and it will teach us interesting things about interstellar chemistry and nothing more. But the silence, intentional or not, leaves room for questions that demand answers. Is the absence of information merely an observational constraint, or is it in some sense part of the message itself? Are we missing the show, or are we unknowingly part of it? Part 6. The Hidden Dynamics. Standing waves in the heliosphere. We need to talk about how energy moves through space, because space isn't empty. That's the first misconception to discard. The region between planets, between Earth and the Sun, between the Sun and the edge of its influence, is filled with plasma. This is matter in its fourth state, beyond solid, liquid, and gas, where electrons have been stripped from atoms, creating a soup of charged particles that responds to magnetic fields in ways that neutral gas never could. The solar wind, that stream of particles flowing constantly outward from the Sun, is plasma. The Earth's magnetosphere, that protective bubble around our planet, is shaped by plasma interactions, and 3I-ATLAS, as it moves through the inner solar system, trails a coma of ionized gas that is itself a plasma structure. Plasma doesn't just sit there, it supports waves, oscillations that propagate through the charged medium the way sound waves move through air or water. These aren't electromagnetic waves like light, they're different beasts entirely, governed by the equations of magnetohydrodynamics, which describe how plasma and magnetic fields interact. When you have two plasma structures interacting, say the solar wind encountering Earth's magnetosphere, or a coronal mass ejection hitting a comet's coma, energy can transfer between them through these wave modes. And here's where it gets interesting. Under the right conditions, those waves can resonate. Think of a tuning fork. Strike it, and it vibrates at a specific frequency determined by its physical properties. Bring a second tuning fork of the same frequency nearby, and it will start vibrating too, even though you didn't strike it. The first fork's vibration couples through the air, and the second fork responds because it naturally wants to oscillate at that frequency. Now scale this up. The Sun and its heliosphere form a system with characteristic frequencies, modes of oscillation determined by the size of the system, the density of the plasma, the strength of magnetic fields. Earth's magnetosphere has its own resonant frequencies, and 3I-ATLAS, with its plasma coma, introduces another oscillating element into this cosmic symphony. The hypothesis we're exploring is that during perihelion, these three systems, the Sun, 3I-ATLAS, and Earth, aligned in such a way that energy could couple between them efficiently. Not through direct connections, there's no physical wire or beam linking them, but through the plasma medium that fills the space between them. When the Sun erupted with coronal mass ejections in late October, those eruptions launched plasma waves into the heliosphere. Normally these waves would propagate outward, spreading and weakening with distance, eventually dissipating into the background solar wind turbulence. But if 3I-ATLAS was positioned at a location where waves reflecting or scattering off its plasma envelope could create standing wave patterns, the situation changes dramatically. A standing wave occurs when two waves of the same frequency, travelling in opposite directions, interfere with each other. The result is a pattern that appears stationary, with nodes where the amplitude is always zero, and antinodes where the amplitude oscillates between maximum positive and negative values. You can see this with a vibrating string. Pluck it and you get a travelling wave, but constrain both ends and pluck it, and you get a standing wave with fixed nodes at the endpoints. In the heliosphere, standing waves can form when solar wind disturbances reflect off planetary magnetospheres or other obstacles. The waves bounce back toward the Sun, interfere with incoming waves, and under the right conditions lock into a resonant pattern that amplifies the oscillation far beyond what the initial disturbance alone would create. If 3I-ATLAS acted as a partial reflector or scatterer of plasma waves during perihelion, and if Earth's magnetosphere was positioned along one of the antinodes of the resulting standing wave pattern, our planet could have experienced plasma and magnetic field oscillations much stronger than the raw solar activity would predict. This is coherent energy redistribution, energy that would normally spread out over a wide solid angle, instead being channeled into specific directions by the wave geometry. It's like how a parabolic mirror can concentrate sunlight to a point hot enough to melt metal, even though the total light energy hasn't increased. The geometry does the work, focusing what was diffuse into something concentrated. The practical implications are significant. Earth's magnetosphere continuously interacts with the solar wind, and it has its own natural frequencies at which it prefers to oscillate. These are called magnetospheric resonances, and they occur at frequencies ranging from fractions of a hertz up to several hertz. When the solar wind buffets the magnetosphere with disturbances at these resonant frequencies, the response is amplified, like pushing that swing at just the right moment. Normally the solar wind is turbulent, carrying energy at a broad spectrum of frequencies, so the resonant amplification is limited. But if a standing wave in the heliosphere were preferentially exciting one of Earth's magnetospheric resonance modes, you could get a much larger response, energy pumping into the magnetosphere at exactly the frequency where it couples most efficiently. From there, the magnetosphere couples to the ionosphere, and this is where speculation moves from plausible to uncertain. We know that magnetospheric disturbances affect the ionosphere. We see it during geomagnetic storms when auroras intensify and the ionosphere becomes highly disturbed. We also know that the ionosphere is not completely isolated from the atmosphere below it. Electric fields can map down magnetic field lines. Energetic particles can precipitate into the upper atmosphere, depositing energy and creating ionization. The question is whether these coupling pathways can affect weather-scale atmospheric processes like hurricane development. Mainstream atmospheric science says no, the energy scales are too small, the coupling too weak. But there are edge cases and poorly understood phenomena that suggest the answer might occasionally be yes under specific conditions. Consider the global electric circuit, a concept that's been around since the early 20th century, but remains incompletely understood. The Earth's surface is negatively charged, the ionosphere is positively charged, and the atmosphere between them acts as a leaky insulator. Thunderstorms act as generators, driving current upward into the ionosphere. This current then flows horizontally through the conductive ionosphere and returns to the surface in fair weather regions, completing the circuit. The entire system is in dynamic equilibrium, with roughly 1,000 thunderstorms active around the globe at any given moment, maintaining the charge separation. Now, if the ionosphere were perturbed by magnetospheric disturbances, that perturbation could affect the global electric circuit. Changes in ionospheric conductivity or potential could alter current flows, which in turn could influence where and how thunderstorms develop. This is highly speculative, and I want to be clear about that. There's no established peer-reviewed mechanism by which magnetospheric disturbances directly control hurricane formation. But there are suggestive observations. Lightning rates in storms have been observed to correlate with cosmic ray flux, which varies with solar activity and geomagnetic conditions. Some studies have found weak correlations between geomagnetic activity and storm intensity, though these are controversial and not widely accepted. The idea that energetic particles precipitating from the magnetosphere could affect cloud microphysics has been proposed but not conclusively demonstrated. What we're suggesting here is that if multiple factors aligned, if a magnetospheric resonance driven by heliospheric standing waves pumped energy into the ionosphere during a period when a developing hurricane was already primed for rapid intensification, the electromagnetic environment could have acted as a catalyst, accelerating processes that were going to happen anyway. The chain of causation is long, and each link is uncertain. Coronal mass ejection creates heliospheric disturbance. 3I-ATLAS modulates that disturbance, creating favourable conditions for standing wave formation. Standing waves focus energy toward Earth. Earth's magnetosphere resonantly responds, amplifying the disturbance beyond baseline expectations. Magnetospheric oscillations perturb the ionosphere. Ionospheric perturbations affect the global electric circuit or directly influence atmospheric electrical processes. Atmospheric electrical changes subtly affect convection or cloud microphysics in a developing storm system. The storm intensifies faster or to greater strength than it otherwise would have. Break any link in that chain and the entire hypothesis collapses. Prove each link and you've uncovered a fundamentally new connection between solar system plasma physics and terrestrial weather, a connection with profound implications for how we understand Earth's place in the cosmic environment. The challenge is that proving or disproving this requires data we largely don't have, and models that don't yet exist. But the fact that we can construct a physically plausible chain of events, even if each step is uncertain, means this isn't just fantasy. It's at the boundary between science and speculation, which is where the most interesting questions always live. Part 7. The acid test. Artificial or natural? There comes a moment in any investigation when you have to apply what's called the acid test, a definitive experiment or observation that distinguishes between competing hypotheses. For 3I-ATLAS, that test involves asking a deceptively simple question. Is this object natural, or was it made by someone? Natural comets follow predictable physics. They're agglomerations of ice, rock, and organic compounds that formed in the early solar system or around other stars. When they approach the sun, solar radiation heats them. Ice sublimates, dust escapes, and the resulting gas and dust coma reflects sunlight, making the comet visible. The pressure of solar radiation and the solar wind pushes this material away from the sun, creating the characteristic tail. After perihelion, assuming the comet survives, it follows its orbital path back to the outer solar system or beyond, gradually fading as it cools and outgassing diminishes. Artificial objects, probes sent by technological civilizations, could be designed to mimic natural comets almost perfectly. A probe intended for long-duration interstellar travel would benefit from a protective outer layer, something to shield sensitive instruments from radiation and micrometeorite impacts during the centuries or millennia of flight through deep space. Ice is an excellent shielding material, abundant in the outer reaches of stellar systems. A civilization building an interstellar probe might deliberately coat it in a thick layer of ice and rock, creating an object that, to external observation, appears indistinguishable from a natural comet. As it approaches a star and the ice ablates, the probe maintains its disguise while potentially gathering data about the stellar system it's passing through. The question is, what observations would reveal the difference? Several candidates suggest themselves. First, trajectory changes that can't be explained by natural forces. Comets do experience non-gravitational acceleration from outgassing, the rocket effect of escaping gas pushing asymmetrically on the nucleus. But this acceleration follows predictable patterns based on the comet's rotation and sun-facing geometry. If a comet suddenly changed direction in ways that outgassing couldn't explain, that would suggest active propulsion. Second, emissions that don't match natural outgassing. Natural comets release water vapour, carbon dioxide, carbon monoxide, various organic compounds, all in ratios determined by the composition of the ice. If a comet emitted narrowband radio signals, or produced jets of material with suspiciously precise timing, or showed thermal signatures inconsistent with passive solar heating, those would be red flags. 3I-ATLAS has already shown some properties that raised eyebrows. The carbon dioxide to water vapour ratio is unusually high, approximately 8:1 based on James Webb Space Telescope observations, reported in preprint papers circulating in the astronomy community. Most solar system comets show the opposite ratio, with water dominating. There are precedent for carbon dioxide-rich comets. They exist, but they're rare. Additionally, polarimetric observations detected what researchers called extreme negative polarization, meaning that light scattered by the dust in the coma showed polarization properties that don't match standard dust grain models. The particles producing this signal are either unusually large, unusually shaped, or composed of materials with unexpected optical properties. Now, neither of these observations proves artificiality. Comets formed around different stars might have different compositions reflecting their birth environments. Interstellar space is cold enough that carbon dioxide could be preferentially retained in some formation scenarios. The polarization anomaly could result from unusual dust aggregation processes or mineral compositions we haven't encountered before in solar system comets. But these oddities mean that 3I-ATLAS doesn't neatly fit into the box labelled normal comet. It's different, and different demands explanation. Avi Loeb, the Harvard astrophysicist who gained prominence arguing that Oumuamua might be artificial, has suggested that the real test comes after perihelion. An artificial probe surviving the intense heat and radiation of close solar passage would likely have thermal management systems, perhaps even active cooling or ablative shielding, designed to sacrifice outer layers while protecting inner components. After perihelion, such a probe might show anomalous acceleration as it heads back out of the solar system, either from deliberate propulsion or from asymmetric heating effects related to its internal structure. Natural comets can also accelerate outbound due to outgassing, but the magnitude and direction of that acceleration should match models based on the observed coma and nucleus properties. Deviations would be significant. Another test involves watching for fragmentation. Comets are fragile objects, loosely bound collections of material that can come apart when stressed by tidal forces or thermal expansion. Many comets that pass close to the Sun break into pieces, either during perihelion or in the days and weeks afterward. If 3I-ATLAS emerges intact, that doesn't prove artificiality. Some comets survive close solar passage without fragmenting. But if it not only survives but shows no signs of the structural stress that typically accompanies such passages, that would be interesting. A well-engineered probe would be designed for structural integrity, able to withstand forces that would shatter a natural comet nucleus. Let's consider motive for a moment. Why would an extraterrestrial civilization send probes to other star systems? Several rationales make sense. Scientific exploration, mapping the galaxy, understanding the diversity of stellar systems and planetary environments. Resource assessment, cataloguing which systems have potentially valuable materials or habitable planets. Long-term communication or beaconing, leaving markers that other civilizations might eventually find. Or something stranger, experiments in stellar engineering, probes that don't just observe but interact with their target systems in ways we can't predict, because we don't share the designer's goals or understanding of physics. If 3I-ATLAS were a probe, its perihelion passage would be the optimal time for close-range observation of the Sun. Any civilization capable of interstellar travel would be intensely interested in stars, both as energy sources and as the dominant physical structures of the galaxy. A probe designed to study stellar physics would want to get close, to measure the solar wind directly, to map magnetic fields, to sample coronal plasma. And if such measurements required active instrumentation, if the probe were emitting particles or fields as part of its scientific program, those emissions might have side effects on nearby planets. The energetic anomalies we've speculated about around Hurricane Melissa and geomagnetic disturbances could be unintended consequences of a probe operating in ways its designers never anticipated would affect a populated planet. This is speculation piled on speculation, I acknowledge that. The more likely explanation remains that 3I-ATLAS is a natural comet with unusual but not impossible properties, that its coincidence with Hurricane Melissa is exactly that, coincidence, and that we're constructing elaborate narratives because the human mind craves explanation and pattern. But the possibility can't be completely dismissed without data, and that data is coming. Over the next several weeks, as 3I-ATLAS emerges from behind the sun and becomes observable again, astronomers around the world will be watching. They'll measure its brightness carefully, looking for unexpected changes. They'll refine its orbit, calculating whether its trajectory shows any deviations from what gravity and normal outgassing would predict. They'll aim spectrographs at it, measuring the composition of its coma to see if the carbon dioxide dominance persists, or if the thermal shock of perihelion altered its outgassing chemistry. Most importantly, they'll watch for anything that doesn't fit, any behaviour that natural comets don't exhibit. Because if 3I-ATLAS is artificial, it will eventually reveal itself, not through dramatic action, but through subtle inconsistencies that accumulate until the natural explanation becomes untenable, and we're forced to confront the reality that we're not alone, and that our visitors are more subtle than we imagined. Part 8. Directed Panspermia. Revisited. There's an idea in astrobiology that's simultaneously elegant and unsettling. Directed panspermia, the hypothesis that life can be deliberately spread between star systems by advanced civilizations. The concept was popularized in the 1970s by Francis Crick, yes, the co-discoverer of DNA structure, and Leslie Orgel. They argued that if life is difficult to start but easy to spread once established, and if intelligence inevitably arises wherever life exists, then the galaxy might be seeded deliberately by civilizations wanting to propagate life beyond their home systems. The mechanism they proposed involved spacecraft, but a more recent variation suggests using comets and asteroids as carriers, especially interstellar ones that travel between stars naturally without requiring propulsion. A 2022 academic paper explored this concept in detail, examining whether interstellar comets could serve as vehicles for directed panspermia. The advantages are considerable. Comets, especially those rich in volatiles like water and carbon dioxide, could protect biological material or precursor molecules from the harsh radiation environment of interstellar space. Ice is an excellent radiation shield. The low temperatures of deep space would keep any dormant life or complex organic molecules in a sort of cryogenic preservation, potentially viable for millions of years. When the comet eventually entered a new stellar system and approached that system's star, solar heating would begin to activate the ice, releasing the preserved material in a region of space where it could potentially reach planets, either through direct comet impacts or through dust grains that decouple from the coma and slowly spiral inward. 3I-ATLAS has properties that purely speculatively make it an interesting candidate for this scenario. Its high carbon dioxide content could indicate an origin in a stellar system very different from ours, perhaps around a star cooler than the Sun, where carbon dioxide ice could condense more readily than water ice. The unusual dust properties revealed by polarimetry might reflect the presence of complex organic molecules or even biological structures, though I need to emphasize that there's zero direct evidence for this. It's pure speculation. But if we're entertaining the directed panspermia hypothesis, we need to ask what signatures might reveal it. What would we observe if 3I-ATLAS were, either intentionally or accidentally, carrying life from another star system? One possibility is unexpected organic chemistry in the coma. Natural comets contain organic molecules. We've detected amino acids and other prebiotic compounds in comet samples and in meteorites from asteroids. But the specific suite of molecules, their chirality, the handedness of their molecular structures, and their relative abundances should reflect natural chemical processes. If 3I-ATLAS showed organic molecules with properties inconsistent with abiotic synthesis, that would be extraordinary. Biologically produced molecules often show strong chirality preferences. Life on Earth is built from left-handed amino acids and right-handed sugars, a pattern that abiotic chemistry wouldn't produce. Detecting such a symmetry in an interstellar comet would be a smoking gun. Another signature might be isotopic ratios. The relative abundances of different isotopes of elements like carbon, nitrogen, and oxygen reflect the nuclear processes in the star systems where those elements formed. Solar system objects have characteristic isotope ratios that tell us about the composition of the solar nebula 4.6 billion years ago. An interstellar comet should have different ratios reflecting its alien origin. We'd expect this, and it wouldn't prove panspermia, only that the comet formed elsewhere. But if the isotope ratios matched patterns associated with biological fractionation, where living organisms preferentially use certain isotopes over others, that would be suggestive of a biological origin for at least some of the comet's material. The most dramatic version of the panspermia hypothesis suggests active release mechanisms, that a seeding comet might not rely on passive dispersal, but could deliberately release payload at optimal times and locations. This veers into the realm where panspermia and artificial probe hypotheses merge. Imagine a probe designed by a civilization that understood biology might emerge elsewhere if seeded properly. The probe travels between stars, its outer layers protecting an inner core of biological material or the chemical building blocks for life. When it enters a new system and identifies a potentially habitable planet, perhaps through passive sensing of the planet's atmospheric spectrum or thermal signature, it times its perihelion passage to maximize material delivery to that planet. The intense heating and outgassing during perihelion would naturally disperse material widely through the inner system. Some would be lost to space, but some, particularly fine dust grains, would be gradually drawn inward by radiation pressure and gravitational effects, eventually entering planetary atmospheres. Earth constantly accretes extraterrestrial material, tens of thousands of tons per year of interplanetary dust particles. These particles are tiny, mostly micrometers in size, and they burn up or gently float down through the atmosphere without causing dramatic effects. But they carry organic molecules, and some scientists speculate that they might have contributed to the origin of life on Earth billions of years ago. If 3I-ATLAS dispersed material during perihelion, and if some of that material eventually reached Earth over the coming months and years, we might see subtle signs. Unusual organic molecules detected in high-altitude atmospheric sampling, anomalies in the chemistry of meteor streams, or more speculatively and frighteningly biological effects that can't be traced to terrestrial sources. This is where the hypothesis becomes almost too unsettling to fully contemplate. Could Hurricane Melissa, or the other anomalies we've discussed, be related not just to physical effects of 3I-ATLAS but to biological ones? Could the energetic environment during perihelion have activated or released something? I want to be absolutely clear that there is no evidence for this. It's the furthest extreme of speculation. But if we're examining all possibilities, we have to at least acknowledge that a comet deliberately designed to seed life might also create environmental disturbances as part of its function. Perhaps altering planetary conditions to make them more hospitable for the life it's seeding. Perhaps testing whether the target planet has existing life that might compete with or nurture the introduced organisms. The implications are staggering and frankly horrifying from a biosecurity standpoint. If alien microorganisms or even just complex organic molecules entered Earth's biosphere, we'd have no immunity, no evolutionary history of adaptation. The outcomes could range from nothing, if the chemistry is simply too different to interact with terrestrial biochemistry, to catastrophic, if the introduced material could outcompete or infect existing life. Science fiction has explored these themes extensively, but the reality is that we have no protocols for dealing with such a scenario. Planetary protection policies focus on preventing Earth life from contaminating other worlds and on carefully handling samples returned from Mars or other bodies where indigenous life might exist. Nobody seriously planned for dealing with interstellar biological contamination because it's always seemed safely in the realm of extreme low-probability events. But 3I-ATLAS is here, and it's real. And if even a tiny fraction of the speculative scenarios we've discussed are accurate, we're in uncharted territory. The next few months will be critical. Atmospheric monitoring programs should be watching for unusual chemistry. Biologists should be alert to any unexplained phenomena in ecosystems, though teasing apart whether something is a new alien introduction versus a natural terrestrial organism we simply hadn't noticed before would be nearly impossible without genetic sequencing revealing completely alien biochemistry. And astronomers should be coordinating with atmospheric scientists and biologists, breaking down the disciplinary silos that normally keep these communities separate. Because if directed panspermia is real, If 3I-ATLAS represents a form of cosmic gardening by intelligences we've never encountered, then understanding what's happening requires combining expertise across fields that rarely collaborate. The alternative is that this is all fantasy, pattern matching run amok, and 3I-ATLAS is nothing more than a fascinating natural comet that will teach us about the chemical diversity of planetary systems around other stars. I genuinely hope that's the case, because the alternative, while intellectually exciting, carries risks we're not prepared to manage. Part 9. The Grand Energetic Harmonic Convergence. Step back for a moment from the specifics of 3I-ATLAS and Hurricane Melissa and consider the larger pattern. Throughout history, certain moments stand out as times when multiple cosmic, solar and terrestrial cycles seem to align, producing events that exceeded normal expectations. The Carrington event of 1859, the most powerful geomagnetic storm in recorded history, occurred during a solar maximum when the Sun was already active, but the specific coronal mass ejection that triggered it was extraordinary even by solar maximum standards. The Tunguska explosion of 1908, where something from space, likely a small asteroid or comet, airburst over Siberia with the force of multiple megatons of TNT, happened during a period of elevated meteor activity. These events were singular, but they weren't completely isolated from broader cosmic contexts. Some researchers have proposed that the solar system experiences periods of heightened interconnection, windows when the normal boundaries between separate phenomena become more permeable. This isn't astrology, it's the recognition that the Sun, planets and smaller bodies form a coupled system where energy and information can flow through multiple channels simultaneously. The Sun's 11-year cycle is well known. Solar activity waxes and wanes in a roughly predictable pattern as the solar magnetic field builds up, becomes unstable, and resets. But that's not the only cycle. The Sun's magnetic field polarity flips every 11 years, so the complete magnetic cycle is 22 years. There are longer periodicities too, cycles of solar activity that span centuries, correlating with climate variations on Earth like the Maunder minimum of the 1600s, when reduced solar activity coincided with the Little Ice Age in Europe. Earth's magnetic field has its own dynamics. The poles wander, moving dozens of miles per year in recent decades. The field strength varies, and geological evidence shows that it occasionally flips, north becoming south and vice versa, though this hasn't happened for 780,000 years. These changes aren't random, they reflect the complex fluid dynamics of Earth's outer core, where the dynamo that generates the field operates. The magnetosphere has resonant frequencies, modes at which it naturally oscillates, and these depend on the magnetosphere's size and shape, which in turn depend on the solar wind pressure. So there's a feedback loop. Solar activity affects the magnetosphere's configuration, which affects its resonant properties, which affects how it responds to further solar disturbances. Now add to this mix the occasional passage of an unusual object through the inner solar system. Comets and asteroids are common, but most are small and follow predictable orbits. Interstellar visitors are rare. Before Oumuamua in 2017, we had never detected one with certainty. Now we have 3 confirmed interstellar objects in just 8 years, and this raises questions about whether we were simply missing them before, because our observing technology wasn't sensitive enough, or whether there's been an increase in the rate at which such objects pass through. If it's the former, then the galaxy is more densely populated with interstellar wanderers than we realised, and Earth is constantly experiencing subtle influences from passing objects that we haven't been tracking. If it's the latter, then we need to ask why the rate might be increasing, whether it's a statistical fluctuation or evidence of something more interesting happening in our local galactic neighbourhood. The concept of harmonic convergence, borrowed loosely from mystical traditions but applied here in a physical sense, is that certain geometric and temporal alignments allow energy to couple between systems more efficiently than at other times. It's resonance on a solar system scale. When 3I-ATLAS reached perihelion at 1.36 astronomical units, Earth was at roughly 1 astronomical unit. The Sun was experiencing elevated activity. The geometry placed Earth, 3I-ATLAS, and active solar regions in a configuration that, if our speculative plasma channeling mechanism has any validity, would maximize coupling. It's not that the comet's presence directly caused anything. Rather, it acted as a lens or amplifier for solar disturbances that were happening anyway, focusing them toward Earth in ways that wouldn't occur without that particular geometric arrangement. Calculate the odds. An interstellar comet passes through the inner solar system, an event that happens at most once every few years based on our current detection rates, possibly less often. It reaches perihelion during a period of elevated solar activity, which covers maybe 30% of the solar cycle. Its orbit is aligned such that Earth and the Sun and the comet form a configuration conducive to plasma wave channeling, which might occur in only a narrow range of geometries. And this happens during hurricane season in the Atlantic when conditions were already primed for storm development, a window of a few months per year. Multiply those probabilities together, and you get something small, maybe 1 in a few thousand or 1 in tens of thousands as a rough order of magnitude estimate. Not impossible, but rare enough that when it does happen, it warrants attention. But here's the philosophical question that underlies this entire investigation. When we observe rare events that seem unlikely but not impossible, how do we decide whether they're meaningful or merely lucky coincidences? Science relies on statistics, on the ability to repeat experiments or observations enough times to determine whether a pattern is real or whether we're seeing randomness. For unique events, solar system scale configurations that happen once in a decade or once in a century, statistics becomes difficult. We have only one Earth, and our detailed observations span only a few decades. We can't rerun the experiment with 3I-ATLAS in a different position and see if Hurricane Melissa still forms. We can only observe, correlate, and model, trying to distinguish signal from noise with limited data. Some scientists argue that this means we should dismiss rare correlations as coincidence, unless we have a robust physical mechanism explaining them. The bar for accepting unusual causation should be high, because the human tendency to find patterns is strong and often misleading. Others argue that dismissing correlations too quickly means we might miss real phenomena simply because they don't fit our current models. The truth probably lies between these extremes. We should be skeptical, demand evidence, require physical plausibility. But we should also remain open to the possibility that the universe operates through connections we haven't yet mapped, that our models are incomplete, and that rare alignments might occasionally produce real effects that transcend coincidence. 3I-ATLAS and the events of late October 2025 might represent one such alignment. Or they might be entirely unrelated phenomena that happen to overlap in time, a cosmic coincidence that our pattern-seeking minds have woven into a narrative. The next test comes as the comet moves away from perihelion, beginning its long journey back toward interstellar space. If the energetic convergence hypothesis has merit, we should see the correlated anomalies diminish in a predictable way as the geometry changes. Magnetometer readings should return to baseline patterns consistent with normal solar wind variations. Seismic activity should revert to its statistical norm. Atmospheric phenomena should match expectations from terrestrial causes alone. If instead the anomalies persist or intensify, that would suggest either a different mechanism or that our understanding of how 3I-ATLAS interacts with the heliosphere is fundamentally wrong. And if new anomalies appear, patterns we didn't predict, that would be the most interesting outcome of all, because it would mean the universe is trying to teach us something we don't yet have the framework to understand. Part 10. The Battle for the Narrative, Science, Secrecy, and Simulation. Every significant astronomical discovery triggers a battle, not with telescopes and equations, but with narratives. Who gets to define what an observation means? How is uncertainty communicated? When does speculation become irresponsible? The case of 3I-ATLAS illustrates these tensions perfectly. Official channels, the Minor Planet Center, NASA's Jet Propulsion Laboratory, have classified it as a comet, designation 3IC 2025-1. The orbital elements are published showing a hyperbolic trajectory with an eccentricity greater than 1, confirming interstellar origin. Observations from multiple telescopes provide data on its brightness, coma characteristics, and spectrum. This is science functioning as designed, data collection, classification, publication in standardized formats that allow other researchers to access and verify the information. But classification is interpretation, and interpretation involves choices. Calling 3I-ATLAS a comet rather than simply an interstellar object emphasizes continuity with known phenomena over its anomalous properties. It's not wrong. The object displays cometary activity with its coma and outgassing. but it's a framing choice that focuses attention on what's familiar rather than what's strange. The unusually high carbon dioxide ratio gets mentioned in technical papers, but doesn't feature prominently in press releases. The polarimetric anomalies are noted but contextualized as interesting rather than paradigm challenging. This is how science normally works, conservatively, emphasizing that new observations fit within existing frameworks until evidence forces revision. But it also means that genuinely anomalous properties can be downplayed or buried in technical details that only specialists read. The question of data access becomes critical. Modern astronomy generates enormous data streams, terabytes per night from survey telescopes, high-resolution spectra from specialized instruments, time series photometry from monitoring programs. Processing this data requires sophisticated pipelines, often incorporating machine learning algorithms to identify objects of interest, flag anomalies, and filter out instrumental artifacts. These pipelines are powerful, but also opaque. An artificial intelligence system trained on thousands of normal comets might automatically flag 3I-ATLAS as a comet and route it through standard processing, potentially missing signatures that don't match its training set. If the unusual properties of 3I-ATLAS were subtle enough, they could be filtered out as noise or simply not, recognized as significant by automated systems designed to handle routine objects. This isn't conspiracy, it's the inevitable consequence of information overload. No human can examine every spectrum of every object in detail. We rely on algorithms to do the initial sorting, bringing only the most interesting cases to human attention. But what if the definition of interesting is based on past experience, and 3I-ATLAS represents something genuinely new that doesn't fit those definitions? It might pass through the data pipeline marked as routine, archived for potential future study but not triggering immediate deep analysis. Amateur astronomers and independent researchers analysing the same publicly available data with different assumptions might spot patterns that the official pipelines missed, not through superior technology, but through different perspectives. There's historical precedent for this. The pulsar discovery I mentioned earlier was almost missed because the signal looked like interference, artificial noise that the automated systems were designed to filter out. Only a graduate student's curiosity about why the interference appeared so regularly led to recognizing it as astrophysical. Fast radio bursts, those mysterious millisecond duration pulses from across the universe, were initially dismissed as instrumental glitches. It took years and multiple independent detections before the astronomical community accepted they were real cosmic phenomena. The lesson is that anomaly detection is hard, especially when the anomaly doesn't match preconceptions about what anomalies should look like. Now layer on the question of secrecy, not necessarily deliberate cover-ups, but the natural classification of information. Space surveillance systems, both civilian and military, track objects in the solar system. Some of this tracking uses assets and techniques that are classified for national security reasons. If a military space tracking facility observed unusual properties of 3I-ATLAS, particularly if those properties suggested artificial origin, that information might not be immediately shared with the civilian astronomical community. The protocols for handling such observations aren't publicly known, but it's reasonable to assume they exist. The tension between scientific openness and national security has existed since the beginning of the space age, and it shapes what gets published and when. There's also the reputational risk factor, suggesting that an astronomical object might be artificial, that it could be an alien probe, is career-threatening in mainstream astronomy. The field has been burned before by sensational claims that turned out to be wrong, and the professional culture strongly rewards caution. Even Avi Loeb, with his tenure at Harvard and established scientific credentials, faced significant pushback when he argued that Oumuamua might not be entirely natural. Most astronomers avoid such speculation publicly, even if they entertain it privately, because the cost of being wrong is much higher than the benefit of being right. If you claim a comet is alien and you're wrong, you're a laughingstock. If you're right, you've made the discovery of the millennium, but the probability seems so low that most rational actors won't take the risk. This creates an environment where the default assumption is always the most conservative interpretation, and deviation from that requires overwhelming evidence. For 3I-ATLAS, overwhelming evidence would be unambiguous artificial signals, radio transmissions, anomalous acceleration that can't be explained by any natural process, or direct observation of structured components that couldn't be natural. Short of that, the object will continue to be classified as a comet, and any unusual properties will be explained as variations within natural parameters, even if those explanations feel strained. The battle for the narrative, then, is between those pushing for recognition of anomalies and those defending the conservative interpretation. Both sides have valid points, and the resolution won't come from argument, but from observation. There's one more layer to consider: the possibility that we're living in a simulation, that the observed universe is not base reality, but a computed environment created by some higher-level intelligence. This sounds like science fiction, but respected physicists take the simulation hypothesis seriously enough to propose tests for it. If we're in a simulation, then anomalies like 3I-ATLAS could be deliberate insertions into the simulation by the operators, tests to see how the simulated inhabitants respond. The energetic effects we've speculated about could be artifacts of the simulation's computational shortcuts, places where the underlying code doesn't perfectly reproduce natural physics. Hurricane Melissa could be both real, in the sense that it caused actual destruction, and artificial, in the sense that it was scripted rather than emergent. I don't actually believe we're in a simulation, or at least I think the question is unanswerable and therefore not particularly useful. But raising it highlights how interpretation depends on metaphysical assumptions. If you believe the universe is purely physical, governed by knowable laws, then 3I-ATLAS must be explicable through those laws, even if we haven't figured out the explanation yet. If you believe intelligence is rare and precious in the universe, then artificial origin seems vanishingly unlikely. If you believe the universe is teeming with civilizations and we're the newcomers who've barely started looking, then finding evidence of alien technology becomes a question of when, not if. These beliefs shape how we interpret ambiguous evidence, and right now, 3I-ATLAS is nothing if not ambiguous. The next few weeks will add data, will narrow the range of possible interpretations, but it's unlikely to fully resolve the question, because extraordinary claims really do require extraordinary evidence, and we may not have instruments sensitive enough or perspectives broad enough to recognize what we're seeing, even if it's right in front of us. Part 11. Quantum Earthquake. AI detects pre-seismic signatures. While 3I-ATLAS was approaching perihelion, another revolution was quietly unfolding in how we understand Earth's interior. In mid-2025, research teams deploying advanced artificial intelligence systems reported success in detecting precursor signals before earthquakes, subtle patterns in seismic noise that human analysts had missed for decades. These systems use deep learning architectures, neural networks trained on years of continuous seismic data from stations around the globe, learning to recognize patterns that correlate with subsequent earthquake activity. The breakthrough wasn't in finding a single simple precursor. Earthquakes are too complex for that, but in identifying combinations of subtle signals across multiple frequencies that collectively indicate heightened probability of imminent rupture. The AI systems look for what seismologists call pre-seismic tremor, low-frequency oscillations that occur in the hours or days before a major earthquake, as stress on a fault approaches the failure threshold. They monitor changes in the ratio of seismic wave velocities, where P waves and S waves travel at slightly different speeds through rock as stress builds. They track variations in electromagnetic signals generated by piezoelectric effects in compressed rock. Individually, none of these signals is reliable. The noise level is high, and similar patterns can occur without subsequent earthquakes. But the AI finds correlations across signals that human pattern recognition misses, weighting multiple weak indicators to produce a combined probability assessment that achieves prediction accuracy significantly better than chance. This development is relevant to our 3I-ATLAS speculation for several reasons. First, it demonstrates that Earth produces detectable signals before major seismic events, signals that exist in the data but require sophisticated analysis to extract from noise. If earthquakes that occurred during the perihelion window had such precursors, and if those precursors themselves showed unusual properties, that might support the hypothesis that external influences were affecting seismic systems. AI trained to recognize normal pre-seismic patterns might flag abnormal patterns that don't fit its training data, potentially revealing external triggers or modulations that wouldn't be visible in conventional analysis. Second, the AI's success highlights how much information exists in continuous monitoring data that we haven't fully exploited. We have magnetometer networks recording Earth's magnetic field continuously. We We have ionospheric monitoring from GPS satellites and ground-based instruments. We have atmospheric sensors, solar wind detectors, seismic arrays, all generating streams of data that are archived but not systematically cross-correlated. What if an AI system trained to find connections between these different data streams could detect coupling between solar activity, magnetospheric disturbances, and terrestrial phenomena like earthquakes or storms? The correlations might be weak, visible only statistically across many events, but if they exist, modern machine learning techniques could find them. There's a project that perfectly embodies this approach, though I should note its exact status in late 2025 is unclear without real-time verification. Let's call it the Global Resonance Detection Initiative, a collaborative effort to apply AI to multi-domain data, looking specifically for correlations between space weather and Earth systems. The hypothesis driving such a project would be that if electromagnetic coupling between the magnetosphere and the solid Earth or atmosphere exists, it should leave fingerprints in the data, coincident anomalies across different measurement types that occur more often than chance would predict. Training an AI system to recognize such coincidences would require careful handling of statistical false positives, but if done rigorously, it could either validate or refute coupling hypotheses with far more power than human analysis alone. Now imagine applying such a system retrospectively to the late October 2025 data. Feed it magnetometer readings from high-latitude stations, include ionospheric data showing total electron content variations, add seismic data from global arrays, include meteorological data, not just surface conditions but upper atmosphere measurements, lightning activity, atmospheric electrical field strengths, include solar wind measurements from spacecraft, coronal observations showing CME timing and characteristics, and include the orbital position of 3I-ATLAS throughout this period. Then ask the AI a simple question. Are there correlations in this data that exceed what random chance would produce? If the answer is yes, if the system identifies coherent patterns linking 3I-ATLAS's position with cascading anomalies in magnetospheric, ionospheric, seismic and atmospheric data, that would be evidence worth taking seriously. The challenge is that such analysis hasn't been done yet, at least not publicly. The systems capable of this kind of multi-domain correlation are only now being developed, and applying them to specific events requires both computational resources and scientific will. But it represents the future of how we'll investigate questions like the 3I-ATLAS hypothesis. Instead of human researchers manually examining data and arguing about interpretations, AI systems will exhaustively search for patterns, quantify their statistical significance, and present findings that can be independently verified. This could democratize anomaly detection, making it harder for subtle signals to be overlooked or dismissed because they don't fit prevailing theories. There's also a philosophical dimension to this development. If AI systems begin detecting real correlations between cosmic events and terrestrial phenomena that human scientists missed, it will force a reckoning with how we validate scientific knowledge. Currently, peer review and human expert judgment are the gold standards, but AI doesn't have intuitions about what's plausible or implausible based on existing theory. It just finds patterns in data. When those patterns challenge existing models, do we trust the AI or the models? The answer should be that we investigate further, design new observations to test the AI's findings, and update our models if the evidence supports it. But scientific culture is conservative, and there will be resistance to accepting AI-discovered correlations that seem to violate established physics. For 3I-ATLAS specifically, the emergence of AI-based anomaly detection in late 2025 is perfectly timed. As the comet continues its outbound trajectory through November and December, researchers have the opportunity to apply these new tools to both real-time and retrospective data. If AI systems begin flagging correlations between the comet's position and terrestrial anomalies, independent teams can verify those findings, building a body of evidence that's either consistent with coupling or reveals the limitations of pattern matching in noisy data. The next few months will be a test case for how 21st century science handles anomalies, whether we can move beyond the limitations of human cognitive bias and theoretical preconceptions to let the data speak more directly. And if the AI finds nothing, if the patterns dissolve under rigorous analysis, then we'll have strong evidence that the 3I-ATLAS hypothesis was indeed seeing faces in clouds, random alignments mistaken for causation. Either outcome advances our understanding, but only if we're willing to look. Part 12. The Solar AI. Helios Watch. Learns to forecast CME chains. The Sun has never been more thoroughly monitored than it is in 2025. Space-based observatories like the Solar Dynamics Observatory capture images across multiple wavelengths every few seconds, building up a continuous record of solar activity with unprecedented temporal and spatial resolution. Ground-based solar telescopes provide complementary data, measuring magnetic fields, spectroscopic signatures of solar plasma, and the detailed structure of active regions where eruptions are most likely. This flood of data creates both an opportunity and a challenge. There's more information about the Sun available than any human team can fully analyse, but extracting actionable predictions from that information requires sophisticated modelling. Enter artificial intelligence, specifically systems, designed to forecast solar activity by learning from historical patterns. These AI systems, and I'll use the name Helios Watch 4 as a representative example, even if the actual systems have different names, apply transformer-based neural networks to solar imagery and magnetic field data. Transformers are the same architecture that powers large language models. They're exceptionally good at finding patterns in sequences and making predictions about what comes next. For solar forecasting, the AI learns to recognize the pre-eruption configurations of active regions, the magnetic field topologies that precede coronal mass ejections, and the characteristic evolution of solar filaments before they erupt. The breakthrough in 2025, according to developments in the field, is prediction of CME chains, cascading eruptions where one CME triggers or enables subsequent eruptions from nearby active regions. This is crucial because chains are more geo-effective than isolated events. Multiple CMIs arriving at Earth in sequence can drive stronger and longer-lasting geomagnetic storms, as the magnetosphere doesn't have time to recover between impacts. Predicting chains has been difficult because the coupling between active regions isn't well understood, but AI systems can detect subtle correlations in how eruptions propagate across the solar surface, learning patterns that aren't captured by current physics-based models. Now connect this to 3I-ATLAS. If AI can predict solar activity more accurately, it can also be used to reconstruct what actually happened during late October 2025 with higher confidence. We have observational data showing that multiple CMEs occurred during the perihelion window, but detailed modelling of their trajectories, arrival times at Earth, and interactions with 3I-ATLAS's plasma environment requires computational resources that weren't applied in real time. An AI system specifically trained to model heliospheric propagation could be tasked with simulating how those CMEs evolved as they travelled outward, whether they merged or remained distinct, and crucially, how they might have interacted with a plasma obstacle at 1.36 AU. The simulation would incorporate 3I-ATLAS's estimated size, composition, and outgassing rate to model its plasma environment. Then it would propagate the observed CMEs through this environment, calculating how the plasma waves and magnetic field disturbances would be modified by their encounter with the comet. Finally, it would continue the propagation to Earth, comparing predicted magnetospheric responses with what was actually observed. If the simulation shows that including 3I-ATLAS in the model significantly improves prediction accuracy compared to simulations that ignore the comet, that would be strong evidence for real coupling. If including the comet makes no difference, then its presence was irrelevant to what Earth experienced. This kind of simulation is computationally expensive, requiring detailed magnetohydrodynamic modelling over vast spatial scales. But it's feasible with current supercomputing resources, and if anyone is taking the coupling hypothesis seriously, such simulation should be underway. The results won't be available immediately. These calculations take weeks or months to set up, run, and analyse. But by early 2026, we should see papers either confirming that 3I-ATLAS had measurable effects on the solar wind structure near Earth, or demonstrating that it didn't. That will be one of the key tests separating speculation from science. There's a broader implication here about how AI is changing our relationship with complex natural systems. The Sun is arguably the most important astronomical object for human civilization. It drives our climate, powers our technology through solar energy, and poses the greatest space weather threat to our infrastructure. Understanding and predicting its behaviour has enormous practical value. Traditional solar physics approaches this through first principles models, solving the equations of plasma physics and magnetism to simulate solar processes. These models have achieved impressive sophistication, but they're limited by computational resources and by incomplete understanding of small-scale processes that cascade into large-scale events. AI offers a complementary approach, learning directly from observational data without requiring complete physical models. The downside is that AI predictions can be opaque. The system makes forecasts but doesn't necessarily explain why in terms humans understand. The upside is that AI can capture patterns that our incomplete physical models miss. For solar forecasting, the optimal approach combines both, using physics-based models to provide structure and interpretability, while using AI to capture the empirical patterns that physics hasn't yet fully explained. This hybrid approach is what systems like Helios Watch 4 embody, and it's proving more accurate than either approach alone. If AI-assisted solar forecasting begins routinely incorporating the positions and properties of unusual objects like 3I-ATLAS into its predictions, that would represent a paradigm shift in how we think about space weather. Currently, space weather forecasting focuses almost exclusively on the Sun and Earth's magnetosphere, treating the space between them as mostly empty. But if objects in that space can modulate or amplify solar disturbances, then accurate forecasting requires tracking those objects too. An interstellar comet becomes not just an astronomical curiosity, but a space weather factor, something that needs to be monitored because its presence affects the electromagnetic environment that Earth experiences. Looking forward, as 3I-ATLAS continues outbound and eventually exits the inner solar system in the coming months, AI systems monitoring solar activity should be able to detect whether the statistical properties of geomagnetic storms change in the absence of the comet. If there was real coupling, storms should be less intense or less frequent for given solar activity levels once 3I-ATLAS is far enough away. If there's no change, then the comet was never a factor. This is a falsifiable prediction, the kind that science demands, and it's one that AI systems are uniquely positioned to test by continuously monitoring and comparing periods with and without the comet's influence. The answer will come not from a single dramatic observation, but from patient statistical analysis over many months, exactly the kind of work that AI excels at and humans find tedious. Part 13. Dark Energy in the Lab. While eyes were pointed skyward at 3I-ATLAS, a different kind of anomaly was emerging in physics laboratories around the world. In mid-2025, a collaboration of researchers working with extremely sensitive Casimir effect apparatus reported transient fluctuations in measured vacuum energy density that couldn't be explained by known sources of noise. The Casimir effect is a quantum mechanical phenomenon where two metal plates placed extremely close together in vacuum experience an attractive force, caused by the fact that certain wavelengths of quantum fluctuations can't exist in the gap between the plates. The energy density of vacuum itself is effectively reduced between the plates compared to the surrounding space, and this difference creates measurable force. What the researchers claimed, and these claims are preliminary and not yet independently verified, is that the Casimir force occasionally showed brief enhancements, lasting milliseconds to seconds, that suggested transient increases in vacuum energy density beyond what quantum field theory predicts. The enhancements were tiny, detectable only because the apparatus was extraordinarily sensitive, built to measure forces at the scale of piconewtons, but they were reproducible across multiple experimental setups in different laboratories, and they showed temporal correlations. When one lab detected an enhancement, others often detected similar enhancements within minutes or hours, despite geographic separation. The obvious question is whether these enhancements are real or artifacts of some uncontrolled environmental variable. Temperature fluctuations can affect measurements at this scale. Seismic noise, electromagnetic interference, variations in local gravitational field from moving masses, all these can create spurious signals. The researchers claim to have ruled out known sources, but establishing that conclusively requires exhaustive analysis. What makes the observation intriguing, at least in the context of our 3I-ATLAS discussion, is the timing. Some of the reported enhancements occurred during late October 2025, coinciding with the perihelion passage. Now, suggesting that an interstellar comet could affect vacuum energy measurements in laboratories on Earth sounds absurd. The scales are wildly different. The comet is an astronomical object operating under classical and plasma physics. The Casimir effect is quantum mechanical, and there's no established theory connecting them. But physics has a history of finding unexpected connections between seemingly disparate phenomena. gravity affects quantum systems, as gravitational wave detectors have to account for quantum noise. Electromagnetic fields can modify vacuum properties, as seen in nonlinear quantum electrodynamics effects near intense lasers or magnetars. The universe is more interconnected than naive reductionism suggests. What if the energetic disturbances we've speculated about around 3I-ATLAS aren't confined to plasma and electromagnetic phenomena? What if they couple into deeper layers of physical reality, affecting the quantum vacuum itself in ways that current theory doesn't predict? This would require new physics, extensions to quantum field theory that allow for dynamic vacuum states influenced by large-scale energy distributions. Such extensions have been proposed in various speculative contexts. Attempts to explain dark energy or modify gravity on cosmological scales often involve fields that permeate vacuum and respond to matter or energy density. If something like that exists, a major energetic event in the heliosphere could potentially create ripples that propagate through this hypothetical field, manifesting as transient vacuum energy fluctuations detectable in sufficiently sensitive experiments. I want to emphasize how speculative this is. There is no accepted theory that would predict such coupling. The observations themselves are not yet firmly established. But the pattern is suggestive. Laboratory quantum experiments showing anomalies at the same time that space weather, atmospheric and geophysical systems show anomalies. If all of these are independent coincidences, that's one thing. If they're somehow connected, that would indicate we're missing something fundamental about how energy and information propagate through physical systems at all scales. The philosophical implication is profound. Modern physics treats different scales and domains as relatively independent. Quantum mechanics governs the microscopic. Classical mechanics and electromagnetism govern the macroscopic. General relativity governs the cosmological. There are connections, quantum phenomena can have macroscopic consequences, and large-scale structure influences local physics through gravity. But generally we expect clean separation. Events on one scale don't directly affect unrelated events on vastly different scales unless there's a clear mechanism. What if that assumption is wrong? What if the universe is more holistic, with correlations spanning scales in ways we haven't detected because we haven't been looking for them? 3I-ATLAS, if it's somehow involved in multi-scale anomalies, would be a probe of this deeper interconnectedness. Not an artificial probe built by aliens, but a natural probe, an unusual object whose passage through the inner solar system creates a test case for physics we don't yet understand. The object itself doesn't need to be exotic. It could be a perfectly normal comet by the standards of interstellar space. What matters is that its interaction with our solar environment creates conditions that reveal hidden aspects of how the universe works. Testing this would require coordinated observation across disciplines that normally don't collaborate. Particle physicists running Casimir experiments would need to timestamp their data with precision comparable to astronomers tracking 3I-ATLAS. Geophysicists recording seismic data would need to share timestamps with magnetosphere researchers. Space weather forecasters would need to coordinate with atmospheric scientists. And all of this data would need to be analysed jointly, looking for correlations that wouldn't be visible in any single dataset. This is hard to organise, it crosses funding boundaries, institutional structures, and disciplinary cultures. But it's exactly what's needed if we want to determine whether the multi-scale anomalies around 3I-ATLAS perihelion are real or illusory. The next opportunity comes as 3I-ATLAS continues its trajectory. If vacuum energy fluctuations in laboratories diminish or cease as the comet moves away, that would be striking. If they continue unchanged, then the correlation was coincidence. And if new laboratories that weren't monitoring during perihelion now begin dedicated observation campaigns, they could provide independent confirmation or refutation. The beautiful thing about physics is that experiments can be repeated, conditions can be controlled, and theories make predictions that can be tested. Even if the initial observations turn out to be artifacts, the process of investigating them rigorously will advance our understanding, either by finding new phenomena or by improving our experimental techniques to eliminate subtle sources of error. Part 14. Project Sentinel. Global Network for Interstellar Monitoring. The passage of 3I-ATLAS has made something clear to the astronomical community. We're not adequately prepared to study interstellar objects. Oumuamua in 2017 was discovered when it was already passing Earth's orbit, on its way out of the solar system. We got only a few weeks of observation before it faded beyond detection limits, nowhere near enough time to deploy specialised observing campaigns or send spacecraft for close-up study. Borisov in 2019 was discovered earlier in its approach, giving more time for observation, but still it was a scramble to coordinate telescope time and spectroscopic resources. 3I-ATLAS was detected months before perihelion, a significant improvement, but even so, the critical observations during perihelion were impossible due to solar conjunction. This has motivated proposals for a dedicated interstellar object monitoring network, often called Project Sentinel, or similar names depending on which institution is proposing it. The concept is straightforward. Deploy a global network of telescopes, optimized for detecting faint, fast-moving objects in the outer solar system, and tracking them as they approach. This requires wide-field imaging to cover large areas of sky, automated detection algorithms to identify candidates, and rapid follow-up capability to characterize objects once detected. Current survey telescopes like the Vera Rubin Observatory, scheduled for full operations in the mid-2020s, will dramatically improve detection rates, but a truly comprehensive interstellar monitoring system needs more than optical telescopes. Imagine a network that includes optical, infrared, and radio telescopes for multi-wavelength characterization. Add spacecraft positioned at various points in the solar system, providing parallax measurements and direct sampling of the space environment around interesting objects. Include magnetometer networks on multiple planets or moons, tracking how interstellar visitors affect the local electromagnetic environment. Incorporate seismic monitoring stations and atmospheric sensors, looking for correlations with terrestrial phenomena. This would be a multidisciplinary, multi-domain system designed not just to detect interstellar objects, but to understand their full impact on the solar system environment. The motivation for such a system goes beyond pure science. If interstellar objects can influence space weather, as we've speculated for 3I-ATLAS, then they become potentially relevant to space situational awareness and planetary defense. An object that disrupts the magnetosphere could affect satellites. If plasma interactions create enhanced radiation environments, astronauts on the International Space Station or future lunar bases could be at risk. And if, even more speculatively, some interstellar objects carry biological material that could affect Earth's biosphere, then early detection and characterization becomes a biosecurity issue. These may be low probability concerns, but they're high consequence enough that spending resources on monitoring makes sense from a risk management perspective. Several technical challenges need solving. Detection algorithms must distinguish true interstellar objects from the much more numerous solar system comets and asteroids. This requires accurate orbital determination, which in turn requires multiple observations over time to establish the trajectory. But interstellar objects move fast relative to the solar system, so there's limited time to collect those observations before the object is past perihelion and heading back to interstellar space. AI and machine learning can help. Systems trained to recognize the characteristic signatures of hyperbolic orbits could flag candidates automatically, prioritizing them for human expert review and dedicated follow-up. Another challenge is coordination. Astronomy has traditionally been a domain where individual telescopes or facilities operate relatively independently, competing for observations of the most interesting targets. A comprehensive interstellar monitoring network requires cooperation and data sharing on a scale that hasn't been achieved before. Observations from different facilities need to be combined quickly to build up a complete picture of an object's properties. This means compatible data formats, agreed-upon standards for classification and communication, and willingness to share proprietary data before publication. The urgency of interstellar object flybys, which can't be rescheduled if an observing opportunity is missed, creates motivation for this kind of collaboration that doesn't exist for most astronomical research. There's also the question of what to do if an object is clearly artificial. Current protocols are vague at best. The United Nations Office for Outer Space Affairs has frameworks for planetary defense against asteroid impacts and for managing radio signals that might be extraterrestrial intelligence, but nothing specific for handling an interstellar probe passing through the solar system. Who makes the decision to attempt communication? What if different nations have different conclusions about an object's origin? The potential for international tension is real, and establishing clear procedures before the situation arises is prudent. This isn't science fiction planning, it's acknowledging that 3 confirmed interstellar objects in 8 years suggest we'll see more, and eventually one might be genuinely anomalous enough that the artificial hypothesis becomes compelling. Looking specifically at 3I-ATLAS, a fully operational Sentinel network would have provided far better data. Spacecraft at different locations could have observed it during perihelion from angles where the sun wasn't an obstacle. Continuous monitoring would have caught any transient behaviours, brief outbursts or trajectory changes that intermittent observation might miss. Coordinated magnetosphere monitoring across Earth, Mars, and other locations would have definitively established whether the comet's passage correlated with electromagnetic anomalies in multiple environments or only on Earth. We can't go back and redo these observations, but we can learn from what we missed and build the infrastructure to do better next time. The timeline for deploying such a network spans years to decades, depending on funding and political will. But components are already being put in place. New survey telescopes are coming online. Spacecraft missions to the outer solar system carry instruments that could contribute to interstellar object characterization. The scientific community is increasingly aware that interstellar visitors are a regular feature of the solar system, not once-per-generation oddities. This awareness is shifting priorities, making the case that monitoring and understanding these objects deserves dedicated resources. And if 3I-ATLAS, through either its scientific returns or the questions it raises, accelerates that shift, it will have served an important purpose regardless of whether the speculative coupling hypotheses turn out to be valid. Part 15. The November re-emergence and the question of meaning. We arrive at the present moment, late October transitioning into November 2025, with 3I-ATLAS emerging from behind the Sun. After weeks of silence during perihelion, the object is becoming observable again from Earth, first to the most powerful telescopes and soon to amateur observers with decent equipment and clear skies. The astronomical community is watching, some out of routine scientific interest, others because they are aware of the speculative hypotheses swirling around this object and want to see whether the data will resolve or deepen the mysteries. What should we watch for? The first and most basic question is whether 3I-ATLAS survived perihelion intact. Comets can fragment from thermal stress or tidal forces during close solar passage. If 3I-ATLAS breaks apart, that tells us about its structural integrity and composition. Fragmentation would produce multiple pieces following slightly different orbits, observable as a string of comet-like objects along the original trajectory. This would be consistent with natural origin. Artificial probes would likely be engineered to survive perihelion without breaking. If the object remains intact, that's interesting but not definitive. Many natural comets survive perihelion, especially those that aren't passing extremely close to the Sun. The next question is brightness. Natural comets typically fade after perihelion, as they move away from the Sun and outgassing declines. The rate of fading depends on the comet's composition and how much material was lost during perihelion. Unusually slow fading or unexpected brightening would be anomalous. If 3I-ATLAS showed active jets or outbursts that couldn't be explained by normal sublimation of ice, that would demand explanation. Artificial objects might have thermal management systems that create observable signatures, though distinguishing those from natural processes would require detailed modelling. Trajectory is crucial. Astronomers will refine 3I-ATLAS's orbit using post-perihelion observations, calculating whether its path matches predictions based on gravitational forces and expected outgassing thrust. Comets often show non-gravitational acceleration from the rocket effect of sublimating ice, preferentially on the sunward side. This is well understood and predictable from observations of the comet's orientation. But if 3I-ATLAS accelerates in ways that don't match outgassing models, that would be the strongest evidence yet for artificial origin. We're talking about deviations that can't be explained by measurement error or unknown outgassing patterns, clear indications of directed thrust or other non-gravitational forces.